So next we have Lorenz Breidenbach, head of R&D at Chainlink Labs, talking about a very exciting and fresh topic, Chainlink's CCIP, cross-chain interoperability protocol, also building the future of TCP/IP of Web3. So that being said, let's welcome to the stage Lorenz.
Perfect. Hey, thanks everyone for having me today, and thanks for the intro, Kun. Appreciate it. So yeah, I'm Lorenz. I'm going to talk to you about Chainlink's cross-chain interoperability protocol, Chainlink's approach to cross-chain bridging. And this is joint work with all of these awesome folks. There's too many to name them, but none of this would have happened without all their input and advice on the design. So shout out to them. So why do we care about cross-chain interoperability? Well, we live in a multi-chain world. Chainlink alone is live on 14 chains today. And Chainlink is live on a heterogeneous set of chains, right? These are all different and unique in their own little ways. Some of them are L1s, some of them are L2s. There's different consensus algorithms underlying them. Some of them use the EVM, some of them don't. So we have a rich and diverse set of chains already today. And I think if there's one thing we can take away from this event, the diversification will only continue, right? We're seeing app chains emerging again as a narrative. We're seeing more L2s, even L3s now. Who knows, maybe one day L4s. So more and more diverse chains emerging. And for all of these chains to be useful, they need to be connected to other systems, to other chains, to move both data, but also value between different chains. Because I think the DeFi narrative is still one of the dominant use cases for blockchains today. And this is borne out by the numbers. So total value bridged to date is something like $168 billion. In fact, that's probably an underestimate because I have to confess that I cribbed these stats from a talk I gave a couple of months ago, so by now they're probably even higher. And over the past 12 months, 68% of that has been bridged. So $115 billion, staggering numbers. And I think that shows an acceleration, if anything. So more value is being bridged across the ecosystem. So based on these numbers, it sounds like a very attractive market to be active in. Why doesn't everyone build a bridge? What could possibly go wrong? Here's a little mood board to show what's been happening in this space. Bridge after bridge has collapsed, just like their metaphorical brethren here. And so what usually happens, right, are security issues. So there have been lots of hacks to these cross-chain bridges. And I think that's because cross-chain protocols are inherently very complex. They're dealing with different chains. They involve distributed systems. They involve cryptography. Lots of things you can get wrong. They also expose a huge attack surface because they're typically running on many public blockchains. They're running over the public internet. And they store vast sums of money. So they're like this giant bug bounty for the entire world to try and exploit. And indeed, we have sophisticated like state-level adversaries trying to hack these bridges and steal money from them. And so I think to date, over $2 billion have been stolen in cross-chain bridge hacks. And just in 2022, so just last year, there have been 8 attacks, $1.3 billion stolen, and over 2/3 of all funds stolen in the blockchain ecosystem in 2022 are from cross-chain hacks. So this is the dominant mode of exploitation today in the ecosystem. So what does that mean? If you want to build a bridge, well, obviously security is paramount. And so indeed for CCIP, for our design goals, end-to-end security is the topmost goal. And that implies a number of things. That implies that we want to minimize complexity of the system because complexity is usually the enemy of security. It means that we want to, at an architectural level, minimize single points of failure. So even if some component fails, it's hopefully not a single point of failure. We want to practice defense in depth. So again, you don't rely on every component being correct all the way. You try to isolate failures as much as possible. And I think another sort of design credo that arises from this is that we say, in this particular context, safety matters more than liveness. So if there's a setting where I have a choice between money being stolen from my bridge or the bridge intermittently losing liveness, I would much rather pick the second. And I can design my system accordingly, as I'll show in the later part of the talk. Then obviously interoperability is another design goal. It's in the name, cross-chain interoperability protocol. We want to connect, as I already mentioned, heterogeneous chains. So we need to be careful about what assumptions we can make about these chains we're connecting here. And we want to be future-proof. So I think the ecosystem will keep evolving. We will keep new chains, new technologies emerging. I don't think that the technology is done or anywhere near done at this stage. And so if we want the system to be successful, we need to be able to evolve it alongside the ecosystem. And then finally, to quote Steve Ballmer, developers, 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 right? This is a developer-facing technology at the end of the day. And so we need to make a great developer experience. And what that means particularly for us is we want to be able to send both arbitrary data as well as value natively at the bridge level. So the bridge is aware of the value that's being transferred. That also has nice implications for security, as we'll see in a bit. We want to provide a single unified API that's easy to use. And I'll show you the API, and I claim it is pretty simple and easy to use. And I'll let you judge whether my claim is true. And then finally, another part of that nice developer experience is that in terms of billing or pricing, I want to have simple, reliable transaction execution. So by way of metaphor, imagine you're mailing a letter at the post office or a parcel. The way this works is you go up to the counter, they weigh your parcel, they tell you, oh, that's going to be $5. You give them $5, and then they worry about the rest. And if the prices of fuel or energy go up after you sent your parcel, you don't worry about that. You already paid for it, and it's going to get delivered. And the same is true here for CCIP. So I don't want users to have to worry about what if the gas price on the destination chain goes up after I sent my message? What if it's underfunded? None of this stuff. So the protocol has to eat that complexity and has to be aware of gas price fluctuations and so on, and has to model these in a way where if I send a message, I get quoted what the price is going to be when I send it, and then thereafter I don't have to worry about it anymore. Fire and forget. Cool. So now let's look at the architecture. No tech talk would be complete without a nice, layer diagram of different components of the system. So here's ours. So at the foundation, we have decentralized Oracle networks running OCR2, a BFT protocol. The details of that don't really matter too much, but the important part is just it's networks of Oracle nodes that run a BFT protocol. On top of that, we have a transport layer that's responsible for securely transporting commitments to information between different chains. And then on top of that, we have the programmable bridge that does all of the nice things for developers, that worries about pricing, that has a unified API, and so on and so forth. And then on top of that, we have the various applications that can use the bridge. On the side here, you see the risk management network. And that's a component that I would argue is unique to CCIP, and that really, I think, bolsters the security claims the system can make. So this is a completely independent, intentionally simple and small system that verifies all activities by the primary system and has to approve them. And if it does not approve, then messages cannot be executed. It also checks for anomalies. So if it detects an anomaly somewhere in the primary system, it can shut the system down immediately. And so I think this is something that, to my knowledge, no other cross-chain protocol has, and that I think greatly reduces various risks associated with operating such a bridge. And in the later part of the talk, we will also see some specific examples that are mitigated by the risk management network. Cool. So let's walk through an example of how a message flows from the source chain to the destination chain, and then along the way, I will explain various things about the protocol, and hopefully you come away with an understanding of how things work under the hood, not just what the high-level user API looks like. So in this example, there are 3 domains, roughly speaking. There's a source blockchain, a destination blockchain, and an off-chain world. In the off-chain world, all of these square boxes abstract away distributed systems of nodes that are running some kind of distributed protocol. And then in our 2 chains here, all of these boxes with a wavy line at the bottom, those are smart contracts. The contracts in white, the sender and receiver, are contracts developed by some external dev. And then the contracts in blue, those are all CCIP components, and similar the off-chain components here as well. Cool. So now let's send a message. We start with the API for sending our message. And so this lives on this router contract, which is this contract right here. That's the single unified entry point to the system. And so you pass to the router contract a struct, which is called EVM to any message. So you can send from an EVM chain here to any other type of chain. And that struct naturally has a receiver address. It carries some arbitrary data that is transmitted to the other side. It carries, because the bridge is value aware, potentially a bunch of tokens and amounts of tokens that are being sent across. And it specifies a fee token that you can use for paying for the message. And this goes back to this reliable payment I had mentioned before. You pay in the fee token, and then you don't need to worry about it anymore. And on the back end, that fee token automatically is converted into Link. And then finally, these extra args, but we don't really need to worry about those too much in the context of this talk. And then you pass this message to the router, and you also specify a destination chain selector to indicate to what other chain you want to go. So you have a single unified router on each chain, and you just tell it, here's a message, please take it to this other chain, and it will handle the rest for you. Cool, so let's keep going with the flow. Sender gives the message to the router, sender is billed, and now the router takes care of appropriately routing the message. So first of all, let's assume that our message has some tokens, and we want to handle those. So what the router will do is it will take the tokens and forward them to an appropriate token pool. There's a token pool instance, this is a contract, for each different token that's supported by CCIP. And so what sort of hides behind this abstraction is that there can be different ways of handling a token. So there might be a token where we just lock it up on the source chain, and then we mint some kind of IOUs basically on the destination chain. There might be a different type of token where we burn the token on the source chain, and then we mint a corresponding amount on the destination chain, and so on and so forth. And different tokens might require different types of special logic, because again, many tokens have their own unique quirks. But behind this abstraction, I can implement all of this on a token-specific level. What also happens here is that the token transfers are rate limited. And I think this is also, to my knowledge at least, unique security feature of CCIP. And what this means is that per unit of time, only a certain amount of token flow is permitted through the system. And this greatly limits the damage that an exploit does, right? So if an attacker manages to exploit the system, they can kind of take up to the rate limit of the tokens, but that's it. They cannot take all of the value out of the system. And so assuming that I have some capability of monitoring the system and shutting things down if I observe an anomaly, I can keep monitoring my system. Let's say the terrible scenario happens that none of us want to happen. Attacker is able to steal some funds. Well, at least they can't take all of the money, right? It's potentially greatly limited how much they can take. And so this is one of the reasons why the system is value aware, because if it weren't, it couldn't do rate limiting, right? But because it knows how much value is flowing through, it can do this, and it can protect against a lot of value being moved in a single attack. So the router then also takes the message, it's forwarded to the appropriate on-ramp contract, and the on-ramp is destination chain specific as well, because the on-ramp performs various types of validation related to the destination chain. So we have different types of destination chains that might have different limitations associated with them. If we think about, for example, Solana, where transactions have to fit inside the size of a UDP packet, I can't have messages that are too large. Or if I think about an EVM chain, then the destination address will be 20 bytes long, and so on and so forth. So I can kind of check that the message is reasonably well-formed. Obviously can't catch all issues that a message might possibly have. But if I catch such an issue, I can revert right away, and I can let the sender know that that message won't be delivered, and provide sort of early feedback to them. The on-ramp also does rate limiting, so it also can flow the aggregate, it can also rate limit the aggregate flow of value that's going to another chain. And again, with the same rationale that we had already discussed, to protect against various types of exploits and mitigate how much damage could be done. And then the on-ramp just emits an event, basically, with a message and metadata. And at this point, we're done on the source chain. So now the kind of real fun starts. So now I need to get the information from the source chain to the destination chain. The first thing I have to do is I have to wait for finality, because I need to prevent double spends, right? So our off-chain system here is going to wait until it sees some new finalized message on the source chain that it has not yet sent a commitment about to the destination chain. Once it observes such a message, it will create a commitment, basically just a Merkle tree and then the corresponding root, and it will sign that, and it will send it to the commit store contract on the destination chain. And all the commit store contract does is it validates that the commitment is signed by a quorum of appropriate members of this committing decentralized Oracle network, and then store the commitment. And then in later stages, I can now form proofs against this Merkle root, and I can show that certain messages are included when I want to execute them. So this is really the kind of security critical step here, or safety critical step of the protocol, because I need to make sure that I only commit to things that indeed happened on the source chain. And so this is the first time where the risk management network comes into play. So what here's an example of this Merkle tree. And maybe another thing that's worth mentioning here is because we use a Merkle tree, right? We can commit to many things at once, and we have a single succinct commitment to all of these messages. And so what that enables us to do is that if we get a whole batch of messages, for example, because the source chain finalize blocks in batches, like, for example, ETH 2.0 consensus does, or various layer 2s do, I can save a lot of cost for the system, because I only need to do this, like I can amortize the cost of committing to messages across many messages. Cool. So now the risk management network comes into play. And I think as I already mentioned, the risk management network is really, I would argue, sort of the most differentiating feature of CCIP. It's a completely separate system, and it only looks at the source chain and destination chain here. It does not actually need to talk to the committing DON, so it's isolated, at least off-chain. And what it will do is it will try to reconstruct the work that the committing DON did. It will try to verify it. And if that fails, then it does nothing at this stage. It does not approve the commit. But if it succeeds, if it gets exactly the same commitment, then it will send an approval transaction to the risk management network contract. And only once a commitment has been relayed via the committing DON and it's been approved by the risk management network, only then do the messages therein become executable. And so what this implies is, first of all, CCIP is fully auditable. Anyone can, by looking at the chain, reconstruct everything that's happening with the commitments and the flow of messages. And also, this risk management network, the software will be runnable by anyone. So anyone can audit on their own whether the system is working correctly and get alerted if there are any issues. So this is probably quite appealing for users of the system. From a security perspective, this is cool now, right? Because if the committing DON is completely compromised, if, for example, there's a key compromise, as we've seen in many of these bridge hacks that have happened over the past years, that's okay. Nothing bad happens. There's maybe a bad commitment in the commit store, but no one can execute the messages therein because the risk management network will not have approved them. Vice versa, if there's an issue with the risk management network, as long as the committing DON is doing its job just fine, there's also no issue. So only if these two independent systems agree, only then can the message progress through the system further. This also protects us against various types of bugs in the committing DON software. So either introduced inadvertently or maybe through a supply chain vulnerability. Again, we have the same property. Only if both systems agree, only then can messages be executed. And so I think this greatly limits the probability that you have the same problem twice, and it greatly mitigates a great deal of risk that is inherent to these systems. This is not a new idea. It's basically called N-version programming. It's from the 80s, like many good ideas. We've seen this applied previously in sort of the aerospace industry with Space Shuttle or maybe the Airbus A320. They actually have a harder problem because for a flight control software, if you're not sure what to do, if two systems disagree, you can't just stop or the plane's going to crash. So they need liveness, but we don't need liveness here. Our problem is simpler, right? If we have a disagreement between the systems, we can just halt, not have liveness anymore, and remediate the situation in due course. A different way of looking at it is also through the lens of TCB minimization, the minimization of the trusted computing base, kind of the code I need to trust the system. So in some sense, this is again a simplified version of n-version programming here, because it's a prover-verifier paradigm we're dealing with, because the risk management network acts as a verifier, kind of that, if you will, verifies the work of the prover of the primary committing donor, the primary system. And so if that work verifies, great, then the system can make progress. And if it doesn't verify, that's fine. Then at least we don't have a safety violation. The overall TCB size of the system is really quite small. So this is an actual implemented thing that's running like this in production. And so in total, for all of the Solidity code that's part of the TCB, we're talking about 3,000 lines of code. And the Rust code, so the risk management network is written in Rust, we're talking about 7,000 lines of code. So in total, 10,000 lines of code, which is quite tractable and much smaller than if you look at the entire size of, for example, the committing DON and all of the other systems that are involved. And the committing DON is written in a different language. It's written in Go. So we really have independence here. We had independent developers work on these systems, and so on and so forth. And then we have a handful of dependencies because, well, there's just some things you can't get around. So I think this really greatly enhances the security already through this approval mechanism, but there's yet another security mechanism that the risk management network introduces, and that is to check for anomalies. So the risk management network knows about certain invariants of the system that should always hold, and if any of those invariants are violated, it will trigger an automatic system-wide shutdown. So what are some examples of these anomalies? Well, the simple one is source chain finality, right? So as I mentioned, in order to prevent double spends, we need to make sure that things happening on the source chain are truly final. And the way this usually works is that either in a kind of more proof of work type setup, you would look at a certain number of confirmations having been mined on top of a block before you consider it final, or now with various proof of stake consensus algorithms, you typically have some sort of mechanism actually where the blockchain node of the chain itself tells you when a block is final. But so if you observe such a final prefix of the chain, if there's ever a fork in that, then it's immediate finality violation, and you don't need to ask further questions. That's a clear cause for concern, and if you see that, the safest thing to do is shut everything down and ask questions later, and that's exactly what happens here. So if the risk management network detects a finality violation in any of the source chains, we trigger an immediate system-wide shutdown. Similarly, execution of an unexpected message. So if, for example, we see that the router on the destination chain executes some message for which there's no corresponding message on the source chain, something has clearly gone very wrong. And again, we take the same approach of shut things down first, ask questions later. So in all of these cases where there's kind of clear anomalies, clear misbehavior of the system, we can implement invariant checks in the risk management network, and if we detect them, shut things down. And so combined with the rate limit, this becomes quite powerful. Because, for example, say an adversary somehow finds an ability to trick the router on the destination chain into sending some wrong message and maybe releasing some tokens from the token pool. They're going to be limited by the rate limit. So say they can take, I don't know, say the rate limit is $10,000 worth of link out of the token pool. And now the risk management network detects, there's a message being executed, there are tokens being moved for which there's no corresponding message on the source chain, and shuts everything down. And so now the attacker made away with $10,000 and everything is shut down. If there hadn't been the rate limit and there hadn't been the risk management network, then they could have just taken everything in the pool, right? Potentially much more. And the way this is implemented is that the risk management network will send kind of shutdown transactions to the risk management network contract with very high gas prices to make sure that they get included. And then all of the other contracts in the system will, whenever they take any action, check a flag on the risk management network contract and ask, hey, has the system been shut down or is everything active? And if that flag is set, then they will just revert and not take any further action. So in this way, even though there's potentially quite a few token pools because we have one token pool per token, right? And there's potentially quite a few off-ramps because we have one off-ramp per source chain here. That's fine. They all just check this one flag, which can be triggered very effectively by the risk management network. And if it's triggered, then we stop. Cool. So that was about the risk management network. Now let's finish the flow of our message through the system here. Let's say it was a benign message, so we have it approved in the risk management network contract, and we also have a corresponding commitment in the commit store. At this point, it's fairly straightforward. So our execution DON just checks, hey, there's a message which is committed in the commit store where we have an approval in the risk management network contract. So now let me furnish a proof of inclusion that message is indeed included in the Merkle root stored in the commit store and send it to the off-ramp. What's worth noting about this is that the executing DON is not a trusted component of the system, really, right? For safety, you don't really need to trust it because if it were to lie about the message, well, then the Merkle proof wouldn't verify. You maybe need to trust it for liveness, but again, that's far less critical than safety. And so in terms of the trusted computing base, this doesn't really figure into the system. The key part is really the risk management network plus the smart contracts. Okay, so the executing DON sent this proof to the off-ramp contract, and now the off-ramp does sort of all of the obvious things. So it verifies the proof against the commit store. There's a check whether the commitment is indeed approved according to the risk management network contract. And then finally, once that's the case, the off-ramp triggers the token pool and the router to release the tokens to the receiver contract, and the router then acts as a single exit point and sends the actual data or payload to the receiver contract as well. And so the receiver contract, in order to know that it's interacting with genuine CCIP, doesn't need to worry about all of these contracts under the hood, right? It just allow lists the router contract, and then it can receive messages from all other chains that are supported by CCIP, whether they're EVM chains or non-EVM chains or whatever else. So again, we have a very simple, unified API. And the way this works concretely in terms of code is that there is a interface that the message receiver here implements. Again, we have the sort of any to EVM message, because now it could be a message from any type of chain going in this example to an EVM chain. And so we just give this message to the CCIP receive function of the contract, and the message contains all of the things you would imagine it contains. So it contains a source chain selector telling you what source chain it came from. It contains a sender that sent the message. It contains data, and it contains the value, like various tokens and their corresponding amounts. Cool. So we saw how the message flows through the system. And we talked about the risk management network. And now I'm very proud to be able to say that this is actually live in production, right? So this is not some design that maybe is going to launch in a year or two, and that is kind of pie in the sky. But this is like concretely how the system works today. This is live. It's live on 4 blockchains right now: Ethereum, Polygon, Avalanche, and Optimism. And it's live right now in an early access phase with 5 initial users, major DeFi protocols like Synthetics and Aave, and then also Flash, Liquidity, Lendvest, and Galaxis. And obviously, that early access phase isn't going to last forever. I'm not going to commit to any timelines here, but expect soon that this will become available to anyone to use. And if you want to use it on testnet and play with it, it's already live there. So on testnet, there's no whitelist, no allow list. Anyone can go and start using the system today. There's also an explorer. It's like a nice UI. If you go to ccip.chain.link, you can do it on your phone, you can do it on your computer. You can see the different lanes, the different chains that are being connected by the system, and you can actually see messages flowing through the system probably right now, if you were to look. That concludes the talk. I hope that you took away a pretty good idea for how the messages are routed through the system. And I hope that I could explain to you how particularly the risk management network and the rate limiting provide unique security features that no other cross-chain protocol provides. I hope that you saw how the design is interoperable, modular, and future-proof, because we can swap out, for example, the token pools or the on-ramps and off-ramps to support future chains, future tokens, future use cases. And I hope, because you saw the actual API, that you're now convinced that it's simple and easy to use. Yeah, thank you very much, and I'm happy to take questions if we have time.